Welcome to this tips and tricks video entitled Mixing Plane Example in Ansys Fluent. In this video, you will learn how to set up a mixing plane model in Ansys Mesher and Ansys Fluent. Let's get started. So here we are in the Ansys Mesher interface. We have a duct here. Here's your inlet, here's your outlet. You can see the name selections are defined. We have a 12-bladed impeller here, which rotates about the z-axis. That has been meshed already with a periodic mesh. We're going to be setting this up in Fluent as a mixing plane problem, and mixing planes problems are very powerful because you can get a steady state solution where you're only modeling a periodic section of a rotating turbomachinery component without having to model all, in this example, there would be 12 blades all the way around, but here we're modeling only one of the blades, so you reduce the meshing requirements. The computational bandwidth is substantially diminished. You can get a good steady state solution. And what the mixing plane model does is it does a circumferential smearing of the velocity field between this 30-degree wedge component and the 360-degree stationary interface for the duct. So it is a powerful tool for turbomachinery, for getting for extracting basic turbomachinery performance data without having to run a full, a full wheel transient sliding mesh model. So let's continue with this setup. So we're gonna insert a name selection here, and we're just gonna call that fluid stat for fluid stationary. Here I'm gonna call that fluid rotating, fluid rot. Okay, and then this is the interesting part. The requirement for the mixing plane is the interface between the 360-degree surface and the 30-degree surface. These should not be defined as interfaces. They have to be pressure inlets and outlets in order to be identifiable by Fluent as candidates for setting up a mixing plane. So here, let's just call that pressure outlet mixing plane. Okay. And then let's go for this surface. And let's call that pressure inlet mixing plane. Okay, I haven't defined any walls. The walls will be automatically assigned when the mesh gets brought into Fluent. So you will have, walls here for, the fluid stat, and then walls here for the impeller blade and the top and bottom volumes, top and bottom surfaces of the rotating volume. Now let's go to the Fluent interface. Okay, so here we are in the Fluent interface. Let's continue with the setup. Okay. So I'm just going to turn on realizable K epsilon as a turbulence model. Okay, let me go to units here. I'm going to change angular velocity from radians per second to RPM. Okay, going to use air as the working fluid. That's the default. Let's go to boundary conditions. For the inlet velocity, I'm just going to do something quick and easy, like 1 meter per second. Leave the turbulence intensity and viscosity ratio as the default. Okay. Now let's go to fluid rot and set up the rotating frame. Okay, so I'm going to do frame motion, and it's about the origin. The rotation axis, the default is along the y-axis, and that is correct. So let's just do 120 RPM. Okay, and now here under domain, we find mixing planes. Okay, so let's set that up. So here you have pressure outlet mixing plane and pressure inlet mixing plane. And now the other thing that you can set up is the number of interpolation points. Let's do, you know, a number like 100. Averaging method can be area or mass. Area is a default. I'm just going to leave it, you know, using area as a default. And now the mixing plane geometry, it wants to know, here it wants to know whether the pressures vary radially or axially on the mixing plane. So here the mixing plane is this way, and you can see that it basically, since it's going to be circumferentially smeared, the mixing plane geometry varies axially. So in the z direction, so let's just click on axial, and now let's create the mixing plane. Okay, and now that is basically it. Let's initialize it. Let's just do a standard initialization with default initial values. And now let's run. Okay, let's do about 100 iterations and calculate. Okay, so now here we are. It's mostly converged. Now let's just look at contours of velocity on the mixing plane. Okay, so there you can see what the velocity contours look like. Let's turn off some lights. Thanks so much for watching.